Okay, so following my previous video in which it was shown, or rather, the analytic continuation of the Riemann zeta function was shown, in this video I would like to first solve the Basel problem, and then afterwards I would like to show that using the analytic continuation of the zeta function we can prove the convergence of the sum, the infinite sum of the natural numbers, which makes no sense, which is why it's so fun. So, what is the Basel problem? The Basel problem is essentially this sum of zeta of 2. Now we define zeta as the infinite sum from 1 to the sum from 1 to infinity of 1 over n to the s, where s are the inputs. In this case it's 1 over n squared. And we don't know, well, I don't know the history of it, I haven't looked it up, but this is something that is to be desired, and you'll see how it's especially to be desired when we begin trying to evaluate later on the sum of the natural numbers. Anyway, the first thing we'll begin with is the Taylor series. So we have a function. This will seem very out of the blue. It will make a lot of sense soon. So we have this sine x, and considering the Taylor series of expansion of this function, we get x minus x cubed over 3 factorial plus x5 over 5 factorial minus dot 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 plus dot 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 blah blah blah. It goes on for a while. Now we can divide both sides, so that becomes sine x over x, and now we instead get 1 minus x squared over 3 factorial, not 2 factorial, 3 factorial plus x to the 4 over 5 factorial minus dot 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 dot. And that's very wonderful. An interesting thing we can see here is if this was to be graphed, and I'm not going to graph it because my writing's already horrible. I can't imagine how bad a drawing would be. But the roots of this function are represented. We can say that x is equal to plus or minus n pi, where n is a member of the natural numbers. That's the worst. I saw black pen, red pen draw it like this. That's probably a better method. Anyway, yeah. So, where n does not equal 0, and n does not equal 0. So, now, if you're familiar with functional ideas analysis, you may have heard of the Weierstrass factorization theorem. And it states that you can express a function as an infinite sum of the product of its roots. An infinite product of its roots, not a sum of a product. So we can say that sine of x over x is equal to big pi from n equals 1 to infinity, aka the product summation of 1 minus x over n pi times 1 minus x over minus n pi, which of course is a difference of two squares, and hence this is equal to n equals 1 to infinity of 1 minus x squared over n squared pi squared. And that is our evaluation for that. If we were to expand the first few terms of this, it is 1 minus x squared over 1 times pi squared times 1 minus x squared over 4 times pi squared, and then 1 minus x squared over 9 times pi squared. And you can see how this gets very big very quickly. We can always pull out a 1 minus x squared here, which would leave us with 1 minus x squared 1 over pi squared plus 1 over 4 pi squared plus 1 over 9 pi squared plus dot 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 plus o x to the 4. 4 should be inside of there. And that's the term that we sort of leave in so that everything works out. Oh, alakazam. Doesn't that look interesting? So, we can then write this as 1 minus x squared over pi squared of a certain sum that we might be interested in. And that's from n equals 1 to infinity of 1 over n squared plus o of x to the 4. Now, what might that be? Whoa! Shock horror. It's this, the zeta function of 2, which we're very interested in because that's the key premise of the problem here. And very near the end of this, to be honest. It's not a very complicated problem to solve. I'm sure it was for whoever solved it the first time round, but now it makes a lot of sense. Now, what we're interested here is we can say that the coefficient of x squared is going to equal what? It's going to equal minus zeta, like that. That's a zeta. Oh god, it's too late. My brain's breaking, over pi squared. And that's going to be our coefficient. That would have x squared next to it. If we expanded our Basel problem fully, because that is the definition of the sum. And so, well, we can compare coefficients, as you do. And we know that our coefficient for x squared, I fear I've written that down wrong. That should be no, that's right. Yeah, our coefficient for x squared. If we label this 2, and we label the above 1, and the one I want to label 1 is the Taylor series expansion. Right at the top, sine x over x. Oh bother! I missed a line. This should be. Sorry, I realised this now. Right, I'm going to say something right at the bottom then. That's 2. Now, what we said earlier was sine x over x is equal to 1 minus x squared over 3 factorial plus x to the 4 over 5 factorial, which is very well and good. But the important bit is that this itself is equal to 1 minus x squared over 6. Bing, ding, 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 ding. Plus x to the 4 over 120 minus dot dot. Ding, 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 ding. That's our coefficient of x squared, and this is going to be equation 1. Now, if we equate our coefficients of x squared here, what we can say is that zeta of 2 minus over zeta of 2 minus over pi squared minus zeta of 2 over pi squared is equal to minus 1 over 6. Very good. So zeta of 2 must be equal to, because those cancel out, pi squared over 6. And that is our solution to the Basel problem, which is going to be very useful right now because we are going to swiftly move on to the evaluation of zeta of minus 1. Now, zeta of minus 1, well, how might that be useful? Now, let's take our natural numbers. So the natural 1, 2, 3, 4, blah 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 blah, all the way up forever. A lot of numbers there, infinite number to be exact. And we can express this as a sum, rather the sum of these numbers. So if we do plus 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 dot dot dot, we can express this as the sum from n equals 1 to infinity of n, right? But zeta function doesn't look like that. It looks like this sum instead. N equals 1 to infinity of 1 over n to the s. But what could s be for us to get that? Well, if you remember your reciprocal rules from whenever you did those, if we let s equal to, we can get from this there, if we let s equal to minus 1. Oh, shock horror, that's why we want to evaluate the zeta of minus 1, because that is the sum from n equals 1 to infinity of n. So very good. Now, if you saw my last video, you will know that the analytic continuation is 2 to the s pi to the s minus 1 sine of pi s over 2 gamma of 1 minus s zeta of 1 minus s. That is valid for all s in C, or in the complex plane, and of course minus 1 is in fact a number in the complex plane, so this function is valid for us, and that would be our zeta of s is equal to this. So now what we want to do is substitute in minus 1. So it's going to be 2 to the minus 1 times pi to the minus 1 times sine of pi times minus 1 over 2 times gamma of minus 1, gamma of 1 minus 1 times zeta of 1 minus s1. There we go, lots of things going on there. We can evaluate some individual components. Well, that's going to be half. It's going to be pi to the minus 2, which would in fact just be 1 over, let's write this as 1 over 2 pi squared just for now. Now we know that sine of minus pi over 2 is minus 1, because that's just a basic trig. I don't know, put it in your calculator if you don't believe me. Pi over 2. Or rather, I can write that as minus 1, and I'm going to do that, times minus 1, times, now we know that gamma of 2 is just 2 minus 1 factorial, which is 1 factorial, which of course is 1, so we can multiply that again by a 1. Now, what did we discover zeta of minus 1 minus minus 1 to be? What is 1 minus minus 1? It's 1 plus 1, which is 2. Wow, puzzle problem. So, we know that zeta of 2 is in fact pi squared over 6, and we are left with minus, we can say that this is equal to, we can say that that's equal to as well, minus 1 over 2 pi squared times pi squared over 6, cancel, 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 that's a 3, that's not a 3, sorry, they multiply together, you don't cancel like that, oh goodness me, is equal to 2 times 6 is of course minus 1 over 2 times 6 is not, 1 over 2 times 1 over 6 is 1 over 12, and we are left with the final answer, and hence we can say that the sum of all of the natural numbers is equal to minus 1 over 12, and it hurts every time I write that, but it is in fact the truth, and we can even put a box around it. So I hope you enjoyed the video, and I will see you next time.